very excited about the next panel. It's entitled Distribution Automation, Volt-VAR Control, and Optimization. With us, we have Mr. Professor Joydeep Mitra from, he is a professor of electric power and energy systems at Michigan State University. I don't know how we feel about Michigan State here, Professor, but welcome nonetheless. We have Burt, Mayor, Head of Marketing and IoT Strategy at Utilidata. Welcome. We have Mr. Wassim Akhdar, Vice President, Product Management at Varentec. Welcome, sir. And Todd Ryan, Director of Regulatory Affairs at SmartWires. Welcome. We are going to begin with Professor Mitra, please.
Okay. Thank you for the introduction. Do I really need the mic, or can I turn to the audience?
You need the mic because it's being webcasted. So,
okay.
Yeah, so we need to. Sorry. But
Speaking to them, back to the audience.
Yeah, they're the audience.
All righty. This works. I hope. Okay.
Lower the mic. So
Yeah.
There we go.
Yeah.
This is, I know that for the, especially Beth just reminded me, for our academic friends, this is a very bizarre setup for you.
It is.
But for the folks in regulatory affairs, you surely know what this setup is. So, so your audience is everybody, because it's being webcasted. I said millions and millions watching this webcast yesterday. But in this forum, in this venue, you address the commissioners, so, and our staff.
Okay. I get it now.
Got it? All
so
right.
Where's the camera? Oh, it's right there. So just make sure. I just need to make sure it's looking at me. So
I think you're good. You're good to go.
All righty. Thank you for that introduction. Thank you, everyone, for being here today. I'm the first speaker on this panel, so I thought it would be best to start out with a very gentle introduction to distribution automation. It's just an overview. As Wassim mentioned, I'm a professor at Michigan State, and I'm director of the Energy Reliability and Security Lab. So if you see this ERISE at the top right-hand corner of the slide, that's what it stands for. And of course, you can tell what the other logo is. Everyone in Ohio is familiar with that other logo. So anyway, an outline to my presentation. I'm going to be introducing what the distribution system is and talking a little about the basics of distribution automation. Particularly, I'll be talking about reliability and self-healing. I feel that reliability is the most important aspect of distribution automation because it started out with a drive to reduce downtimes. And there's this fancy word called self-healing, but I'll tell you what it is in a moment. I'll talk about distributed energy resources and microgrids, which are an important part of distribution automation, and about flexible loads. And I'll talk briefly about controls for distribution automation. The Volt-VAR controls are an important part of this panel, but I'm told that other speakers will address it in quite a bit of depth, so I'll just give you a top-level view. So I like to introduce the grid using this slide, which I stole from the NERC website. But it's a very useful slide in that it demarcates the functional parts of the power system, namely the generating system, which is marked in black here. And we are talking about centralized generation, not wind farms and solar parks. And then the transmission system is marked in blue here. We're talking about high voltage transmission over long distances. You'll see the voltage levels marked there. Probably everyone here has at some point heard that higher voltages amount to lower losses. So when we have to transmit power over long distances, we use higher voltages. And then the part on the right, marked in green, is the distribution system. That is basically the retail part of the grid, as I like to refer to it. And that is the part that we are going to be dealing with today. And I'll talk about distribution automation. The important thing about the distribution system is that is where the system connects to the end user. I like to supplement that slide with this graphic. I created this graphic myself, so there's no credits here on the slide. I like to use this to emphasize that the grid, as we refer to it, is basically the bulk power system. Most power engineers do not include the distribution system in the grid, but important though it is, because it's not really networked as such. The bulk power system, which consists of centralized generators, those are the squigglies in that figure, and the transformers, the double squigglies facing each other, those are the transformers. So the generators step up, generate power, and the transformers step it up to transmission levels. And the transmission system is networked. So I showed alternative paths there showing it as a grid. And then the sub-transmission system is that part that bridges the transmission system with, or the bulk power system, or the grid on the left, with the distribution system where we have the end users. End users, those who get primary loads, mostly three-phase, and then there are secondary loads, which are mostly single-phase. We talk about distributed energy resources, that's distributed generation and storages. Those plug into the distribution system. Coming to distribution automation, the motivation for distribution automation, as I said initially, was basically to provide higher reliability, reduce downtimes. But the main operational features of distribution automation include advanced sensing, protection, and restoration, so that if anything goes wrong, we restore as much power as possible, as quickly as possible to the customers. Then there's an integration of distributed energy resources, which could be owned by the utility or the consumer, depending on what the model is in that part of the system. And the other thing is flexible loads that I'll talk about soon. We've dealt with demand side management before, and we've also heard about demand response. It's heading toward what the new term that is being applied is flexible loads, and I'll talk about that briefly in a moment. The technological and regulatory enablers. Oh, before I go on to that, there are also those who believe that distribution automation can also contribute to market participation of the distribution system, but I do not think that is an essential feature, so I'm going to skip that in the interest of time. So I have that grayed out. In the technological and regulatory enablers part also, I have that bullet point grayed out. We've heard of DMS or DSCADA. DMS stands for Distribution Management Systems, which contain the DSCADA, which stands for Distribution Supervisory Control and Data Acquisition System. It acquires data and sends back control signals through communication infrastructures. We've heard of AMI, the Advanced Metering Infrastructure, and the DR, the Demand Response Infrastructure, whereby the control center sends out real-time pricing signals to the customer. It's been realized to different extents so far. Most of the grid in the US doesn't have it in place yet, where we send real-time pricing signals to the customer and the loads respond to that. But much of the utility is looking in that direction. I'm not going to read this out, but we've seen these potential benefits to utilities and customers, claimed by the so-called smart grid movement. And again, featured on top here is higher reliability, shorter and less frequent outages. So I'm going to use this one slide to explain what it is, how we achieve that in using distribution automation. So traditionally, distribution systems have had this kind of a structure that I show here. That transformer on top is the distribution substation, and then we have a recloser, which basically senses a fault condition. And when there's a fault in the system, it opens it, but a recloser also has, unlike traditional relays and circuit breakers, a recloser has the ability to close back on itself in a timed or programmed manner. But then most traditional distribution systems have fuses. We are trying to move away from that and put in more reclosers. So if you look at the center figure, we've replaced a few of the fuses with reclosers. It's expensive to replace all fuses with reclosers. So, on a few key feeders, we've done that. And in the end of that, on the right side, there's a grayed out link between the top feeder and the bottom feeder, a link that did not exist on the left figure, the traditional figure. Okay, so that recloser ties the two feeders, and that's one aspect of distribution automation. Now there's a very simplified representation. So if you look at the rightmost figure, this illustrates how this reliability and self-healing thing works. If you look at that red section and that thunderbolt-like thing in the figure shows a fault. So there's a fault in that somewhere in the middle section. Traditionally, if there's a fault, then what's going to happen is that one of the fuses is going to blow upstream of that fault, and everything downstream gets disconnected. But in an automated scenario, what happens now is the recloser in red, that opens up, but that grayed out recloser in the middle figure, now you see it in blue, which means it closes now and provides an alternative path to pretty much as many customers as possible. Now, if there are customers on that middle segment that's in red, they might suffer, but we try to minimize the outage to the number of customers. The other aspect of this is we need a lot of sensing equipment as well, because in the past, as you know, utilities depend on customers calling in their outages. Okay, but with sensors, they automatically know when there are outages and respond to this with an automated system like that. So this is the most important part of distribution automation. It's a work in progress. As I said, replacing all fuses with reclosers is an expensive proposition. So it'll be a while before we get there, really. But in key parts of the system, we are already doing that. Some utilities are more advanced than others in this. That brings me to the next item, which is DER, distributed energy resources and microgrids. On the right of the slide, you'll see everything we include within the scope of distributed energy resources. And on the left, there's a graphic that was envisaged by the US Department of Energy many years ago when they defined the term microgrids to mean a small part of the grid that works independently or in connection with the grid. So it's a small grid, so to speak, but that is usually at in the distribution system. Here are some key benefits of distributed energy resources. I'm not going to run down this list. I'll give you a moment to look through this, but it does offer many features at close to the end user level, and again, the ability to plug in user resources and provide reliability differentiated products and services, use of combined heat and power. And many of you know that this CHP business, it dates back to the days of the PERPA. I know I'm out of time. I'm going to, I don't have too much left. So, but we started late, so hopefully you condone that. Again, here are some drivers of microgrid adoption. Okay, different sectors of consumers are adopting microgrids at different rates. And CHP has been around for ages. Like I said, it dates back to the days of the PERPA. And there's actually a database that I've listed on this presentation where you can look at all the CHP facilities that have been installed and are in use throughout the United States. There are also microgrids proliferating throughout the system. The Midwest has been a little slow, but is catching up. This is, a future a vision of a future smart home where you have all kinds of small scale generation and storage. You'll see there's a battery bank in the basement. And again, this is how distributed energy resources are going to penetrate all the way down to the customer level. I'm going to move on to flexible loads. This figure shows how, in an extreme scenario, we move from the traditional operation paradigm where generation, the load is assumed to be determined by the customer. So the customer demands power, and the generation keeps track of it and follows it. So we used to call it load following. It is, some proponents say that we are going to shift to a generation following scenario where with so much variability in renewable generation, where we don't have much control over the generation, the load will follow the generation rather than the other way around. So that gives us the notion of flexible loads, where we can store power and use it when we don't have generation from the grid, or we can back down our loads. So it's an extreme form of demand response. Smart appliances in the home are an enabling feature for this. They can operate during off-peak, low-price periods. They also can respond to price signals, real-time price signals from the utilities, and make sure that they consume more power in the less expensive periods, and so on. The byproduct of this adoption is that consumers end up using newer and more efficient technologies as well. So that is a secondary means of reducing of energy efficiency and environmental impact. Very briefly, all this requires sophisticated control at the distribution control center. So a control center should have communication with all these devices that have been deployed throughout the system. As an example, fuses don't need to communicate. A fuse senses a high current situation, a fault situation, it blows. But if you have remote sensing capabilities to report back outages or other things like high voltages and abnormal operating conditions, that needs to be communicated back to the control center, and the control center needs to send out signals to control various devices. So the control software needs to have a lot of capability in terms of network visualization. Modern control centers have large displays showing at every instant what is going on the grid, on the distribution center system, if it's a distribution system control center. So network visualization, state estimation, which tries to estimate the condition of the system from all the measurements that it has been receiving. Power flow analysis has to do with calculating how much power is flowing in the various components in the system. Forecasting demand and utility operations management. Volt-VAR control, which I'll come to in a minute, but won't spend too much time on because speakers after this will build on it. Protection and remedial action. I talked about the reliability and the operation of reclosers and fuses. Management of crew resources is another important aspect of distribution system control because the operation is going to get a lot more complex. Very briefly now, coming to Volt-VAR control, what it is the need to control voltage and reactive power. VAR stands for volt amperes reactive. So reactive power is power that doesn't really consume energy as such, but it's out there. There are components out there that suck up reactive power, and you have to make sure there's enough of it. Otherwise, you have all kinds of nasty things happening to the system. And you have to make sure there's enough voltage available to meet the safety and standard requirements. So Volt-VAR optimization now has to do with looking at all the system equipment and how they can be controlled in order to satisfy things like reducing losses in the system, making sure that voltages throughout the system remain as far as possible within acceptable limits and so on. And this is achieved by controlling system equipment. In the past, it used to be restricted to transmission systems, but of late, this has grown into the distribution arena as well. And we try to reduce losses primarily through Volt-VAR control. Volt-VAR control, as I said, is achieved by controlling these three kinds of devices in the system. One is capacitors and other devices that inject reactive power into the system, and load tap changers and voltage controllers, voltage regulators that adjust the voltage in different parts of the system. I've shown some images here. I'm going to skip this because the next few speakers are going to elaborate on these, but I'll give you a moment to run through this list of benefits of Volt-VAR control. That brings me to the conclusion of my presentation, where I would like to say that distribution systems are important in that they connect the energy supply system to the customer. However, in the past, it has traditionally lagged the rest of the system in terms of modernization and upgrade, because there are so many parts to that distribution system, so many load points. So it's very important to prioritize which ones you're going to upgrade first and modernize. So because of this profusion of devices and connections, it's been a humongous challenge to upgrade distribution systems. However, there's a tremendous potential that people are recognizing now, and so there's been some change, but we've just touched the tip of the iceberg. I'd like to conclude by saying that I've kept this presentation by a very introductory and not go on to some of the deeper issues such as data management, cybersecurity, interoperability, which I know from the agenda that others have touched upon before, and the speakers here onward will also elaborate on later, but I wanted to keep this introductory in nature to give you a broad level overview. Thank you very much.
Thank you, Professor. Appreciate it very much. Actually, we will field questions when all the panelists are done with their presentations. So thank you so much.
Very good.
Appreciate it. Mr. Meyer.
Thank you. Well, many thanks for having me today. I was here as a listener for phase one, and so I'm particularly excited to be back with the opportunity to speak directly to the Commission about Volt-VAR optimization control. For a little context, I'm in from Providence. Utilidata is a Providence-based software company. We've had AEP Ohio as a strong partner for the better part of a decade. Have, as part of GridSmart Phase 2, are deploying on over 160 circuits with them, which will serve 120,000 customers here in Ohio. Similarly, work with a large number of the other largest investor-owned utilities in the U.S. to provide VVO and conservation voltage reduction software solutions. So I'll talk some, at the risk of repeating Joydeep, I'll talk some about the basics of VVO and CBR. I'll warn you, I'm decidedly not an electrical engineer, so I'll explain things in the terms that have made it intuitive to me. The what, why, and how of VVO, why we do it, and how things are changing moving forward. And then want to spend the bulk of my time speaking about the broader set of considerations that surround Volt-VAR optimization. It touches on many of the themes we've heard both yesterday and in phase one around IT, OT, convergence, and communications infrastructure, cybersecurity. If I can leave you with one message today, it's to not consider VVO in a silo, as a singular, independent application lumped in among many others for a distribution management system or a DERMS. That in fact, it can and should be considered sort of at the nexus of a lot of these themes we've been talking about. So what's the context? Why do we have to do anything about voltage? Well, there are a few underlying realities. One is the utility has to deliver acceptable voltage within standards, within bounds, at all points along the grid, and also at all times of the year, under all loading conditions. And in fact, that voltage conditions aren't consistent across the line. We see losses over the course of the line, through devices, as they're dropped to homes and businesses. And meanwhile, there's also uncertainty about loading conditions, about when people turn things on and off throughout the day. So I am frequently overwhelmed with the mass of acronyms in this space, particularly in VVO. It's often used interchangeably with VVC, with CVR. I'll explain a little bit just for a moment about how these things are different from each other. And the easy way to understand it, VVO is about the optimization of the voltage curve. It's essentially about reducing the losses, flattening out this curve. CVR is about lowering the curve entirely. It's about dropping down voltage while it's still above that minimum bound, that 114 volts is delivered to a residence. But it turns out that when you deliver lower voltage for many loads, that means things use less energy. And that's your energy efficiency play. So I'll pause for a moment and say that VVO and CVR are not particular technologies. It's an objective. There are multiple different ways to achieve VVO and CVR. Utilidata has a particular approach to this that we like for a number of reasons, but I won't go into depth on the different ways to do this, or the advantages of our approach versus others, or debate the merits of different technologies for VVO and CVR. EPRI has this great animation that really shows how the flattening and the lowering of the curves are interrelated, are really kind of two sides of the same coin. So you see this blue line here, that's voltage losses. As we add a meter at the end of the line, we now have the information that allows us to lower voltage. That's CVR. Now we'll introduce these two orange things. Those are capacitor banks, which allow us to inject reactive power, which further flattens the curve, minimizes those line losses. Then we can perform CVR again and lower it again. Now we're going to add this green box, this midline voltage regulator, which allows us to step up the voltage midway along the line. And now we can do CVR again. So essentially what we've done from that first blue line to this new green line is we've flattened and lowered. And that's how those two things are related to each other. So why do we do it? Oftentimes it gets reduced to VVO is for energy efficiency. In fact, there's a wide range of benefits. There's a lot of things that come with this lowering and flattening. So first and foremost among them is grid stability. For anyone that's concerned with keeping the lights on, with equipment not failing, and in fact with customer devices being able to operate most effectively and efficiently. That means operating at a consistent voltage and at a low voltage where possible within those bounds. For CVR, we do see those energy efficiency benefits. We see oftentimes with utility, we see in the range of 3 or 4% demand reduction. That corresponds not just to lower energy bills, but also to carbon emissions reduction, where that's a part of the generation mix. So one thing I'll stress about VVO and the landscape of energy efficiency, one thing that differentiates this is it doesn't require any sort of customer behavior change. So things like demand reduction, things like energy efficiency, like light bulb switches, this requires a change on the part of the customer. They're critical elements of grid modernization, but require some element of behavior change. I have to change my light bulb. I have to now use my air conditioner in a different way than I did before. In the case of VVO, no one sees that anything has changed other than a 3 to 5% reduction in their bill. So how is this done? Very briefly, there's sort of 4 traditional devices that are used to regulate the reactive power and the voltage. In the substation, this is called a load tap changer and a voltage regulator. Along the feeder, this is a midline regulator and a capacitor bank, which is what injects that reactive power. We now increasingly see these devices at the grid edge, which allow us to manage volts and VARs. So things like smart inverters with rooftop solar panels, also hardware placed at the edge of the grid that can autonomously regulate some of those volt-VARs. You'll likely hear more about from Wassim. So how is the world of VVO changing? And this is where it connects with some of the other panels that you've heard. The growing challenge is in distributed generation. So the grid was built for one-way power flows. Now we have power being produced from the grid edge. Particularly on circuits with high penetration of rooftop solar, this can wreak havoc. This creates instability, volatility that needs to be managed for a well-functioning distribution grid. Similarly, it produces challenges for rigid predictive models. The models were built to help us understand and control conditions in a world that's rapidly changing as we add more and more rooftop solar. We also, though, have these new opportunities. Technology advances allow us to manage that problem. And that's sort of two-pronged. One is communications infrastructure, we've heard a lot about. Increasingly, we can we can listen from the devices in the field and understand what's going on. We also have a greater ability to take action based on what we hear from those devices. So advances in digital signal processing and machine learning, how we do the analytics on that data, allows us to manage this increasingly complex distribution grid in real time. So now I'll shift gears a little bit to some considerations. And apologies, this is going to echo a lot of the things that we heard yesterday from Brad and John and in phase one as well. I know there was a great discussion around future-proofing in the last panel, and I think Chairman Hawk hit it on the head, that this is of critical concern and is also really difficult. I'll add that as we look across different industries, historically, a first-order simple answer is software versus hardware. When you have hardware, you have to replace it. When you have software, you just have to upgrade it. Similarly, we can think about models on a spectrum. And more rigid predictive models will, as we incorporate new technologies, new business models into the grid, and we don't yet know what all of those new technologies will look like, those models require updating. So to the extent that we can benefit from those advances I mentioned in communications infrastructure, in data analytics, that allows us to rely less on rigid modeling-based solutions and more on responding in real time to what we see on the grid. At the risk of beating this platform concept to death, I see no future scenario in which things don't get tied together, where it's a collection of point solutions that are managed independently of one another. It seems for operators, a platform-based solution will allow for technology synergies. Brad talked a lot about this yesterday, about allowing data streams and technologies to speak together and empower one another. For grid operators, it makes things much easier than switching back and forth between lots of different applications. I'm not an expert on distributed energy. Suffice it to say that in terms of distribution grid management, it brings both challenges and opportunities. On circuits, particularly we're seeing in Hawaii is the cutting edge of this. There are many challenges that come with high penetration of solar PV. On the volatility and fluctuations that I mentioned. We also have an ability increasingly to manage Volt-VAR with those smart inverters. I'll say that it seems likely that you're going to need to harmonize those two systems. You won't have smart inverters at the grid edge that are managing Volt-VAR independently of how the grid equipment is being managed, those capacitor banks and voltage regulators to manage the power quality on the actual primary. Lastly, and I want to spend a little bit of time touching on cybersecurity, because that's not a conversation that generally happens in parallel with VVO. In fact, it's usually a different conference altogether with different people speaking a different language. But in truth, security on the OT side is really the other side of the same coin as optimization. And I'll tell you a little bit about why that is. So this slide has a ton of text. There's no need to read it, except to say that this problem of managing optimization in a world where there's so much uncertainty is really hard, and there are a lot of people thinking about it. I really like this top quote, which I think actually came from a critical infrastructure, a grid security forum, but works the same way. It says that some of the technologies for infrastructure we'll have to support, that we're going to have to support, haven't been invented yet. That's kind of like building an airplane without knowing how far it's going to have to fly or how many people it's going to have to carry. That we're in somewhat of a similar position, and it's tough to make investments around that uncertainty. So if you look at the literature, this question is tackled, or is at least confronted. How do you optimize with so much uncertainty? And the emerging consensus is flexibility, is that you have the ability to respond to things, to manage as conditions change in ways that you may not be able to predict. So hold on to that as we pivot to cybersecurity, and bear with me here for this jump. So I promise it'll connect. So we did an exercise in-house where we wanted to understand what, in this new world of interconnected, addressable devices on the grid, what are the things that we should be concerned about, that grid operators and regulators should be worried about? And the answer, as you'll see from the overwhelming number of boxes on this slide, is a lot. There's a large number of devices which are newly addressable and newly hackable from remote location. And there's obviously an enormous amount of complexity that goes behind this, but can be orchestrated in such a way to do damage and produce negative outcomes. So how do we even begin to address this problem? Well, we again looked at the literature, and in a totally different language, they answer this question in much the same way, security experts, that it's about visibility. The common denominator in any sort of attack on critical infrastructure, cyber-physical attack, so not an IT attack on data, but things are happening that shouldn't be happening. Physical equipment is being used in a way that is detrimental to the grid. So they would explain this as the one way to combat it is to have visibility, signals-based visibility into the behavior or operations of the grid, and they would say you need to federate that or combine it with a network-based security like SCADA networking monitoring, so that you can see the commands that are being sent and then also what's physically happening in real time. I want to plug really quickly this guy, Mike Lasante, who was actually the chief security officer at AEP Ohio, spent a bunch of time at Idaho National Labs before that, is now at the SANS Institute, because I think he has reduced this in the most simple way and talks about its implications for the grid and makes the jump over to optimization as well. He talks about the importance of looking at physical behavior of the grid, at these signals. He uses this digital ghost concept to mean really looking at the process in real time. And he describes how we have this depth of expertise in optimization. We understand how these things should be working together, and so that means that we are really well positioned to see when they're not working together. When things aren't behaving in an optimal fashion, that could mean one of two things. Either there's an asset failure, which is valuable because it can inform predictive maintenance, it can inform how we deploy crews, or it means a potential cyber threat, an anomaly. So really, it's the same intelligence, it's the same insight that allows us to optimize, to manage things effectively, as allows us to see when things are going wrong. Both of those things rely on these other elements of grid modernization, the communications that let us talk to all of these devices in real time, and the data analytics and standards that allow us to understand and derive value from that data. So I'll leave you with, I generally stop at a picture of Providence, where we're based. Instead, I'll show you this cool new toy that we just built that we're really excited about just a couple weeks ago. That is a 3D hologram of the city of Providence, where and this is, I should say, is used to illustrate these concepts of visibility that I've been talking about, and real-time communications and insight. We can overlay in real-time distribution conditions on top of the city of Providence and see how things are behaving in real time. I have no clue whether or how this will ever be valuable for anything, but I think it's very cool to place on a tabletop. So thanks very much for your time. Appreciate it.
Thank you. Thank you very much. Mr. Akhdar.
Good morning, and thanks for the opportunity to speak in front of you today. So I mean, you've heard a lot of stuff so far about VVC and CVR, right? So what I'm going to cover today is what we call next generation CVR, which is really, it's the same concept. It's reducing voltage to capture energy savings and energy waste reduction, but the approach is totally different. It's really using power electronics that are located on the LV side of the network. It's closer to the customer, but it's a fully owned and operated by utilities. So again, I'm not going to cover the concepts because it's really been covered already. So I'm just going to go through high-level starting point. So is it a low-cost, effective energy saving or energy efficiency resource? The answer is yes. The cost of CVR is around 2 cents kilowatt of energy saved. So if you look at that in terms of overall the efficiency programs that we have, it's very low on the scale. It's very competitive. And if you look at it from added generation perspective, that's very competitive as well. So the cost is there. Is it scalable? This is the second question. And the answer is yes. I'm quoting a study from 2010, PNNL, where they talk about overall, if CVR is deployed national-wide, you're looking at about 3% reduction in energy consumption in the U.S., which is huge. The third question is does the technology deliver? And also the answer is yes. There's been a number of smart grid demonstrations so far, and if you look at the results that are coming back, it's consistently talking about between 1% to 3% energy reduction from these CVR programs. And this is, again, CVR programs that, this is what I call traditional programs, and we're going to talk about later how, our or the LV technology actually takes these benefits to the next kind of level. And in the end of the day, what does it really, who benefits from that? And then the number one beneficiary of this is the end customers, because what you end up having is lower customer bills, because it's a simple concept of lower voltage yields lower energy consumption. And this is without changing any consumer habits or any demand reduction programs out there. So this is with the same consumption habits, you're going to end up saving the end customer money. And at the same time, from an operational perspective, maybe this is too close to me. The operational perspective, you're basically operating more efficiently, and you're reducing wasted energy in the network. So just to walk through, how does it start and where we are today. So typically the power kind of distribution has been you supply as high of a power out of the substation, so your lowest end or lowest voltage customer has voltage within the NC limit, which is 114 volts. So you end up, for example, 125, 120, 24 volts out of substation, so your end or the lowest end customer is going to have 115 or 114 volts. So that CVR came in, or traditional CVR came in, and this is what Burt kind of explained, that you have the medium voltage equipment that you put in. So you put cap banks and LVR, where basically you try to reduce that slope by adding these peaks in, or adding these boosts throughout the distribution system, where basically you reduce the slope of that drop, and it enables you to reduce the overall voltage coming out of substation, and eventually reducing the power consumption. So what's the limitation of that approach? Number one, if you look at the left-hand slide, the assumption behind the CVR programs has been that the energy is reduced as you go down the feeder, and most of the low voltage customers are towards the end of the feeder. What we've seen, if you look at the right-hand side from data we collected, is that this is not entirely true. You could have low voltage pockets of customers anywhere in the feeder. Could be in the beginning, in the middle, or in the end of the feeder. And that type of condition, the MV equipment can't really resolve that issue fully. So you end up with these clusters of customers really controlling how far can you take the energy savings. So again, that kind of situation is not fully solved by the traditional VVC today. And the second point is, tackling technical losses throughout the service transformers. This is also not addressed by the cab banks and the LVRs that are on the feeder. And the third point is that for a traditional VVC approach, you need some sort of visibility into the feeder. You need either AMI systems to be involved or to be installed, or you need to install sensors in the feeder. The second dimension to this is, how fast does the traditional VVC or CBR react today? So you're looking at a system, for example, that you really analyzes and issues control every 15 minutes. You're looking at primary or MV equipment like LTCs and cab banks that needs up to a minute to react. Versus look for example the LV Varentec solution, where you're going to have power electronics that on a sub-cycle basis you're monitoring and controlling the voltage near where the customer is. So as we go further, and we talked a lot about new types of load, PVs, DERs. These type of loads require dynamic voltage support. So the traditional VVC approach is not as adequate as we move forward to be able to give the customer that power quality that they require. So you need that type of fast-acting equipment. If you're living next to a big load or aggregation load or whatever it is, if this load is picking up and sagging your power, you need that kind of electronics next to your transformer or to where you are to be able to compensate. So you wouldn't see flickers, you wouldn't see voltage sags until the primary equipment operates. And the other aspect is that the primary equipment is not, if it's operating all the time to kind of manage fluctuations, you're actually sometimes over operating this equipment. So basically these units would shield from the primary side or the MV side all these voltage fluctuations from all these new type of loads that you have. So again, just to summarize what the next generation VVC is. So what we saw, again, this is, you see it on the picture there. So this is power electronics equipment that we put on the secondary side of a distribution transformer. And what we found throughout the projects we have done before is that it actually enables an additional 1 to 3% of energy savings on top of what has been typically kind of accomplished with traditional CBR systems. The other point is, again, I kind of talked about it, is the sub-cycle dynamic change. So this is power electronics. This is, their monitoring and controlling. So which actually gives the customer or the end customer the power quality for any changes or fluctuations in the loads. We've had projects where we had, customers had a lot of voltage kind of flickers because of different loads that they live next to, and we were able to bring them within the 2.5% that they require in terms of flickering voltage on their end lines. And the other kind of aspect that we're going to talk a bit before later on is enabling DER. So we had, I'm going to talk later about HECO. We had a very successful project with HECO where we were able to, create enough voltage room to pretty much almost double their PV penetration, PV capacity on the feeders that they tested it on. So also that's a great advantage in terms of when you start bringing in these DER and PV installations to the feeder. In terms of the technology itself, another kind of benefit to it is it's fully distributed. It doesn't rely on any other systems to be in place. And there's been a lot of talk today and yesterday about data, about needing to model the LV network. This type of solution doesn't need any model. The data itself, it's very minimal in terms of data coming back, because that system, you give it the objective, it sits there, and it actually monitors and controls locally. So things like disaster, if you have these natural disasters, if you have loss of communications, it doesn't need that central system that controls all these units. It actually, you incrementally get benefits as you deploy these units. So there's no prerequisites for it. So the more units you bring in, the incremental benefits you start kind of harvesting. Did I forget anything else? Yeah, it's fast deployment. Basically, you hang it and it's running. And again, it doesn't need. In this case, you can start implementing CVR without having to have an AMI system in place or add a new sensors in place or any DMS system or GS system to be added. This is just a kind of, just to give you a flavor of what the system does. I'm not going to go too much into the details of it, but if you look, the first kind of, section where you have, if you look at the voltage throughout the day, how it fluctuates, right? So it goes, I can't see that far, it goes from maybe 125 to very close to 130, 115 maybe volts. Now, when we activate the system, which is the second part of it, you can see that how closely, and this is real-time data, so you see how closely the voltage is kept to its set point, which is the yellow line that just shows just below these points. And again, the whole concept is once you get that, you get the third section there where you get the room to be able to drop the whole voltage and really capture all these benefits. So this is what we try to kind of claim as the new smart voltage standard, right? You flatten the voltage throughout the feeder, and in a way you maximize your energy efficiency and you minimize your wasted energy or losses in the distribution grid. This is, again, not to go too technical, just to also give you kind of another flavor of how the system operates. So the top left, or number one quadrant, you'll see the blue line, this is a substation voltage. And the orange and red line, this is the points across the feeder capturing voltage. And you see that the spread of these points, right? So this is the way it is. And then the second one, which is the right-hand, top right-hand side, you reduce the voltage by 3%, which is typically CVR would do. And you can see all these red points now, they're exceeding the NC limit, which is 114, and you're getting all kinds of violations throughout the day. So what happens in the number 3 is that we activated our, we call them angles, our Varentec kind of LV devices. And then you can see how consistently the voltage has been kind of close to the substation volt has been brought up. And now you have an extra room beyond the 3% that you can drop. And this is quadrant number 4, where you can actually drop it another 2%. So you can capture the whole 5% of the voltage. And again, keep in mind, this is a system that's distributed. You put it on the grid. This is not, you don't need any, AMI systems to be in place to be able to capture that, or DMSs or GIS. This is, we typically do a study overall of the pockets in the network where you have low voltage, and we know exactly where to target, and we can end up with such results on the grid. This is also to give you kind of a flavor or kind of a flavor of what the solution is really about, right? The core component of it is the hardware devices that you can see on the screen on the right-hand side, on the left-hand side, where this device itself has very high resolution sensing, has a sub-cycle control, and basically it tries to maintain the voltage to the voltage set point that you give it. And on top of that, there is basically a software platform that does analytics, and it does analytics, and it does basically diagnostics on these units. And these units talk to this software platform either via cellular connections or via AMI mesh networks. So you leverage the infrastructure, the AMI infrastructure, communication infrastructure that you have. And the software side of it gives you, again, if there's communications issues, if there's low voltage, gives you analytics, it reports back, and it also allows you to change the objectives. So in cases, for example, you have an emergency peak and you want to reduce below for a certain short time, maybe instead of 114, you want to make it 112. You can do that on an emergency kind of basis, and you can send it through a software platform. And the third piece is what I kind of touched on is the engineering analysis. So we typically look at the network overall, and we are able to first of all know where we need to deploy these units. And there was some discussion this morning about how do you know the value ahead of time. We can actually predict for each substation how much voltage we can reduce, and we can kind of through an on-off kind of testing, we can predict how much energy savings you will be able to achieve. Now, in terms of again, it's an emerging technology, but it's been deployed over 22 utilities today. We have over 1,300 devices running in over 22 utilities, And so we're beyond just proof of concept, or the solution has been proven, and we're moving into a type of full-scale projects. I kind of picked 2 projects that we're kind of working on, just happening today. So just to give you a flavor of what utilities are looking at. So one of them is Excel, where they call it SVC, which is secondary VAR compensators. It has been approved by Colorado PUC, part of their AGIS, which is Advanced Grid Intelligence and Security Initiative. So this is part of a full-blown CVR program that they have. And in case of HECO, I'm going to touch on it on a slide later. We also had a very successful pilot or project with HECO where, and I took that code from their grid modernization plan that just came out a couple of weeks ago. And it talks about, it talks actually singles out Varentec in this case. It talks about, deploying 61 units on the feeder, and how it actually stabilizes or improve the reliability, and also talks about allowing the hosted capacity to go from 5 megawatt to 7 megawatts on that specific feeder. So again, in terms of on top of improving reliability of the network and the power quality, you also are creating this new space to include more DER and PV. This, just to show also, this is an example of HECO, what we've done. Just to give you an example, but how the system kind of work in a very, very high level. I'm not going to go into details. What you see is the first kind of section where this is before what you call angle off, which is our devices just observing, being passive, not operating. And you can see the voltage spread, along the feeder, right? So let me just actually explain what these are. The first line is the actual voltage observed at the locations we're monitoring. The second line is how much VARs it's injecting. Without going too technical, basically the idea, if it's 0, that means the unit is passive, is not really doing anything, and it goes, and then as it goes to 10 being fully engaged. This is doing its best to push the voltage up. The third line, which is the red line, this is the solar radiance in that area. So as you can see, as the solar picks up, you can see that the top line, which is the voltage, it's also going up, even though typically the load would go up. But that PV production is offsetting the loading. And this is where they're having a problem, where during the day, you're getting very close to the limit. And this is why you can't bring in more PV solar, because right now you're hitting the ceiling. So if you look at the second side, where we activated our units, and you can see how hard they're working, and then you can see how much we kind of be able to reduce the voltage band or fluctuation during the day. And that enabled us, which is the third piece, to drop the overall voltage in the feeder and see that white space above it. This is the room that we created to be able to integrate more PV. So roughly, gives you an idea how the system works. And one thing also we found out is it operated well during the day, but also at nighttime. If you look at the first picture with the nighttime, because your solar drops all the way, and your consumption like around, 6 or 7 o'clock, where people come back home, you have no more solar penetration, but you also have the load picking up. Our units were there, and we're able to also at nighttime to adjust that load to make it also to compensate for the increased demand and low PV production. And I'm not going to touch too much on because there's the idea also being dynamic, because we also find in some cases you have a kind of a cloud cover that comes over, and the whole PV drops suddenly, even though you have high loads. So in these cases, if you have primary equipment, it would take time to pick up, and you experience voltage lags. In that case, our system is there and pretty much instantaneously picks up and raises the voltage back up. And that's just to leave you with that slide. Basically, it's what we call, our solution is win-win-win, right? It's win for utilities, where you can get a rate of return in case you have, loss of revenue adjustment mechanism in there. You would have deferred CapEx investment in asset upgrades, because right now, instead of upgrading your assets to kind of accommodate for more load, what you do is you're investing in this type of program to get efficiency, which defers your need to invest in new capex. And it also gives from a efficiency and reliability. You're getting better efficiency and reliability in the system. You're getting better power quality delivered to the customer. And the last point is you're enabling DER integration. From a customer perspective, you get lower bills, obviously, without changing in behavior. You're getting ability to integrate more PV capacity, and you're getting better quality. You wouldn't experiencing flickers or low voltage. From a society overall, obviously you get reduced environmental impact and lower carbon footprint, but you're also getting a levelized cost of energy. Basically, that's very competitive. It's between 1 to 2.5 cents per kilowatt compared, again, from an efficiency perspective, you're looking for around 4.6 for energy efficiency programs. And from a new power generation kind of perspective, you're looking between, $3 to $15 per kilowatt hours in this case. Thank you.
Thank you very much, Mr. Akhdar. Mr. Ryan.
Thank you much, Chairman. Thank you, commissioners, staff. Really appreciate the opportunity of being here, and thank you everyone who's viewing in locally and remotely. Very much looking forward to talking with everyone today. My name is Todd Ryan. I'm Director of Regulatory Affairs for SmartWires, and I'm going to be a little bit different than the rest of the panelists in that our technology primarily is on the transmission network, not the distribution network. But we have a very common theme to the other panelists in the sense that we're trying to get more out of the current infrastructure and trying to optimize the infrastructure we have today. But before I kind of jump into what we do, I like to try to align anyone who I'm talking to about a presentation about our technology with kind of what some of the impacts of what we're seeing today in our changing grid and how it's actually affecting you today, right? A lot of these panels, we can talk very academically about what the future holds, but it's hard to understand what it really means for the grid today and the problems we're seeing today. And the answer is that rapidly changing generation means that we don't know where our centralized generation is going to be at necessarily in 5 or 10 years. That together with unpredictable load growth, net of all these technologies on the end of the grid, means that we don't necessarily know where our load is going to grow. And so if you don't know where those two objects are, how are we supposed to know how to connect those together with a sound 40-year investment or even 60-year investment? That on top of the fact that so much of our economy today is being driven by data centers and the need to always have Twitter at our fingertips means that we have greater uncertainty, but higher expectations from our customers. So we got to do better with less certain information, all while trying to make sure that we're being sensitive to our, end of the day, the real customers. Are we building in a respectful manner? Are we being environmentally responsible? So all these additional constraints have real implications for utility planners today that maybe don't always get as much recognition as they should. It's a really tough job to be in today, and we work with our customers every day, and we see how difficult this job is. And the results are that we have more needs on the transmission system today that are short-term needs. A year, it maybe lasts for 2 years, 4 years, 6 years, 8 years. We may not even be certain how long it's going to last, but we know one thing, that transmission need isn't always going to be needed. And that's a difficult thing to justify a reconductor or a rebuild when you know that the need is going to disappear, right? We have what we're calling emergency transmission needs. It may take 2 years to reconductor a line, but a plant can retire in 90 days. What are you going to do if that retirement causes reliability overloads, reliability needs, right? Traditional solutions make it really difficult to invest in our grid to meet those types of needs. We're seeing more bubble projects. Any fans of NCAA here? Bubble teams that may or may not make it. Maybe their bubble is going to burst. These are reliability projects that at 101% loading, 1% overload, the project is needed, and at 99, they're not. And small changes to assumptions of energy efficiency, demand response, where EVs are going to grow, or whether or not a construction project is on time, or retirement schedules, all these things affect whether or not that transmission project is really truly needed or when it's needed. And so these are all real transmission needs that we're seeing today with our customers that we only predict are going to be more and more frequent and make it more difficult for planners to decide what is the best investment, and more difficult for you yourselves to understand whether or not your utility is prudently investing in their grid. And so what we're finding is that we need to be more flexible, right? Common theme today in our technologies. We need to come up with more innovative solutions on how to solve these unique challenges. And more importantly, increase collaboration. It's no longer that you can just hand the utility a bunch of data, a spec sheet, and expect a creative solution to come out. It's really about working closely with our utility partners. I think, again, a theme I think we hear a lot today, to make sure that we're working together to solve the issue, right? Utility can't be an expert on solar and voltage conservation and reduction and power flow and know everything, right? We need to help make each other smart and work together to collaborate. And so that's really what we do at the heart of it, is we try to enable our utility partners. Another thing that I'd like to point out is that when possible, I'd like to speak about a broad set of categories of transmission technologies. I know you don't have time to have every technology up here in front of you, but I want you to make you aware that there's a large set of technologies out there that do one key thing, which is get more out of the current grid. And these technologies are particularly well suited to those short-term needs, those emergency needs, those near-term needs, or the bubble needs that are difficult to invest today. So advanced power flow control, dynamic line rating, advanced conductors, AEP's bold technology, all of these technologies get more out of the current right-of-ways and get more out of our current system. And smart wires is just one of them. So I want to speak just briefly about how we're partnering with our utility clients. It really is key that we work closely with them. And really what we're doing is we're bringing them into the fold from the very beginning in terms of product specification, testing, piloting, from soup to nuts of our product development to actual picking and selection of projects and deployment and construction. We're working with them at every step. And what this allows us to do is actually build better technology faster. Kind of like Apple, every 18 months, a new technology, a new model, a new iPhone. And it's really allowed us to create a technology that's both scalable and modular, meaning that you can tune the investment directly to the need size, both for today and tomorrow. It's redeployable, so if your need disappears, like a short-term need, you can move them to a new need. And plug and play, meaning that you're not going to have to rerun protection studies and not have to worry about utility communication protocols or any kind of standards, IEEE standards. Our technology, because it's been developed with utilities from the beginning, it immediately plugs and plays into their system. So we've been working with utilities around the world and in the United States, particularly on development of projects, and hope to give you some examples shortly. So what does our technology do? I've so far just kind of been talking around what the box does for utilities, but what is the actual box? Here is what we call the grandma slide. Hopefully this means that Chairman Hawk can explain it to his grandma when we're done with this today. Here you have a planning study, traditional meshed transmission system with a 5% overload in some distant future date. Now, in the near term, you can redispatch generation. Long term, you could rebuild, you could build a new line, you could reconductor. But you can also use power flow control, and our power line guardian goes on that constrained or predicted to be overloaded line and pushes power away onto underutilized transmission capacity, underutilized transmission paths. And these underutilized lines exist all over the world. Every transmission system has it because of the inherent methods we use to plan using N-1 security constraints. Our second technology is called the power router. It can both push and pull. And so you can put it on the constrained line and push power away, or you can put it on the underutilized lines and pull power towards it. And so this one elegant function of just being able to push and pull power away or around transmission constraints has an incredible number of applications. It could be as simple as just reliability, or purely based on economics, providing cheaper power to load, or it can be more specific to specific utility challenges. be it sensitive construction, helping to extend outage windows to construct a sensitive line, to renewable integration. So we have 3 technologies. The Powerline Guardian is our first technology developed with RPE and knee-track. It can push and it clamps directly to the conductor. And then we have 2 newer, bigger versions, the Power Guardian that is can be deployed on towers or substations that also pushes, and the Power Router that pushes and pulls. So one of the key things that we are looking to partner with utilities, and we're able to develop these technologies so quickly because we have amazing people and amazing resources on our staff that are able to innovate in a way and nimbly adapt to what our customers are telling us faster than any other vendor could be able to do. And that allows us to create innovative solutions. So Kristen, if you could probably press play, I'm not sure that my clicking is going to do it. This is an example of an innovative solution using our first technology, the Powerline Guardian, with Pacific Gas and Electric, a key partners of ours. We were set to do a pilot on Livermore, California with our first technology, and we couldn't do the traditional installation because of a endangered species limited our ability to roll trucks and do a traditional bucket truck. But we were able to work with our partner closely, and this is a helicopter installation. So no boots touched the ground, no trucks rolled onto the actual transmission site, and you can see our Powerline Guardian being clamped on the conductor, and for each individual unit, it took 6 minutes from takeoff to touchdown to install. This is obviously a shortened video, but it was the credible work by the PG&E team, and they said it was one of the easiest things that they've ever installed. And so we were able to do a pilot demonstration deployment in less than a week, and we would have been, which is equivalent to about a month or less to do a full reconductor, which is order of magnitude faster than actually doing a reconductor. Another customer of ours has a very sensitive set of customers to building. And what we were able to do when we worked in hand with them is be able to create a different way of deploying our devices that were just limited them only to one span. And we were able to build that span in the least visible section of the line, the easiest place to build. And so that not only improves reliability, but it also keeps your customers happy. In other cases, we've worked with utility customers on the concept of converting existing towers into what we're calling smart towers. So the ability just with few modifications to add our devices to existing towers. Again, eliminating a lot of the headache around permitting of a reconductor of a new line. You can use the current infrastructure you have, especially if substation space is limited. We've also worked with customers to develop substation-based, or what we're calling the smart bank. The idea, again, if you need to build a new light substation to accommodate our device, pick the easiest part of your line to build, or put it inside the substation fence and deploy our devices in this modular fashion. And finally, we're working on a mobile solution, right? So you can imagine this to be able to help construction, or to be able to respond in an emergency, or a number of other applications that our utility clients have suggested. Wow, this would be really great if you could just roll up a truck and bring smart wires in to help us out of this jam. So we're listening to our customers, and we're going to be able to deploy a mobile device in the very short time frame. And this all leads, like if you're following the train of thought of being able to respond to short-term needs, bubble projects, emergency needs, it can really lead to a new way of thinking about investing in our grid. No longer do you need a 7-year timeline. No longer do you need to think of your investments as sunk once you've made them, right? So here's a quick vignette of how you can see our devices are redeployable, quickly deployed, have optionality in terms of investment over time, and can meet these short-term needs. This is a hypothetical grid where we kind of proactively build in a few locations based on our utility customers' expected needs. And they expect wind to come on and create an overload. You bring our devices in to solve that overload, but how much of the wind in the queue is actually going to show up? That might be a particularly windy place, but it's still uncertain based on our queue reforms, how much of that wind is actually going to materialize. But you can, as wind materializes, you can add more devices. Say you need to import power, right? You need more transfer capability from one side of your grid to the other. Well, you can bring our devices in to bring more power in. Well, what if a plant retires? That might cause an overload. Well, or a new plant comes online, that might and you may not need to import as much. Well, you can move our devices from one location to another to address that. Really, again, just the ability to get more out of your grid and be redeployable breaks down a lot of the standard assumptions in planning transmission. So with that, I'd like to just say that I use the analogy a lot of times of highways, right? We all understand traffic. We all hate traffic. You know, there is a time and place where you need to build new roads. And there's a time and place for encouraging customer behavioral changes like carpooling, right? But there's also a need for real-time data and navigation, right? To get around traffic, get more out of your current grid. And that's what we do. And that's what a lot of other technologies can enable, is getting more out of your grid. So with that, I'll yield our time for discussion.
Thank you very much. Appreciated all those presentations. So we've got, we'll call it about 10 minutes here, since we got started a little late. I'd like to open things up to staff first here. These are items that I think, especially on the cost recovery side, are items that I think you guys would probably contend with first and foremost. So let me start with staff. Christina, do you have anything you wanted to? Tim, who's sporting a beard, I'm going to start calling you Evil Tim with that beard. Do you have a question or two?
Thank you, Mr. Chairman.
Yep.
Quick question for Wassim.
Yeah.
How many devices generally do you have to put out on a feeder? Is it one device per transformer, or are they strategically placed?
Yeah, so it's one device next to a transformer, but it was not at every single transformer. So typically, it depends on the need of the feeder itself, but typically you're looking at, could be a dozen devices on a feeder, you know, could be 20, could be 10. So it's the order of magnitude depends on the need or how bad is the voltage issues are. But no, definitely not at every single transformer, no.
Okay, thank you.
Jake? Okay. Dan?
Just a quick, more technical question for Todd and for Wassim. I took it that the devices that your companies provide can be deployed without the need to integrate them into communication systems. They work autonomously to do their jobs. Did I get that correctly?
Can I get that first?
So our devices do have the ability to respond autonomously to explanatory variables like current or loading, line loading. But we do have the ability as well to communicate back to the substation and back to the EMS system to allow them to be dispatched by the utility or by, in this case, PJM on a more granular basis. So it really is, again, we respond to what our customers' needs are and our sense, how they would like to control them.
And Wassim,
Yeah, in case of Varentec, you're right, that device is operating on its own out there, doesn't need to communicate back. However, we have the communication capability to the platform that we have to do basic diagnostics and to do what I mentioned about emergency. If you want to push the voltage lower, you have a way to push an emergency voltage lower.
maybe that answers the real question, which is how do you know when the devices are no longer working?
There you go, yeah.
So the utility is able to know that your device, after they've installed it, has failed or isn't operating properly, and so they get a signal for either to investigate or to repair and maintain.
So yeah, number one could be communication issues. Number two could be even diagnostics on the device if there's any issues to need maintenance or you have pay attention to. But also we send information back to the platform to be able to do analytics on top of that.
Okay. Todd? Beth?
Wassim, I was wondering if you could talk a little bit about these demonstration projects. You mentioned there's 26 that you've been involved with. Are those in different states? Is there multiple in different states, or can you just give us some background on that?
Sure. The 26 actually on the first slide, that was overall the smart grid projects of CVR, which is not what are Varentec's projects. I don't remember which slide is actually 22 utilities I mentioned that we're involved in. So it's really, the concept of voltage control, again, this is what we do, but it's the objective or the use case is different, right? Because in cases where you have, the public power market, the use case is not energy efficiency as much as peak demand reduction. So in that case, what we do is we really reduce voltage for a certain amount of time to be able to shave that peak. And the economic use case is straightforward because you can say for so much investment, this is how much you're saving in terms of peak reduction. So that's one market that we are kind of involved in, mostly in the Midwest, I would say, utilities. Now, the other use case is energy efficiencies, which I kind of try to focus on for this kind of setting because it's more relevant. So again, this is 24-hour, 7 days a week. You try to minimize or get the most efficiency out of the system. And the third use case that we're seeing, and I talked about Hawaii in that case, where we try to support DERs and allow for this room for PV, because in the case of Hawaii, they got to a ceiling that they can't enable any more PV. So you can give them that room that you integrate without affecting the reliability or the power quality of the end customer.
Were the projects initiated by the utility, by a commission, or how did they come about?
I think it varies in a number of cases. In cases of the public power, obviously it's utilities because you can easily justify the economics. You don't need a rate case or anything like that, right? Because you can show costs versus benefits, and as long as the costs, or the benefits overweigh the costs, you're good to go. I mentioned Excel. Excel is a case where it's really the PUC. So Excel kind of had this business case, and they went through the rate case, and the PUC approved that. So Colorado is an example of an energy efficiency type of program. And Hawaii itself, it wasn't initiated at this point by the PUC, but the PUC has the mandate that they have to get, I think, 100% penetration by 2030, I believe. So there was a mandate by the PUC, or an objective that HECO in that case we were engaged with to be able to meet that objective. Did that answer your question?
Yeah, so it's sort of a mixture, it sounds like. So is it vary according to the area, how many units you have to deploy in order to make a good demonstration? Or is there a rule of thumb of how many?
I mean, there's a rule of thumb, which is typically it's like 6 units per megawatt peak, but it depends on the substation, how heavily loaded are these feeders.
Okay.
So what we do before we do any investment in the field, we get whatever the utility have in terms of planning data, whether it's SIME or whatever system they have. Even if there's AMI network, that's good because we can get the AMI voltages. We have a team that basically has the tools. They input the data. It comes out with, for that substation, you need X amount of units in these so we know the exact location we have to put them in. And we run simulations to be able to predict how much we can reduce the voltage and eventually how much you reduce the energy saved. And once you go through that, we do a pilot to make sure, our predictions are typically, we come conservative in terms of prediction. So once you do this pilot and do a proof of concept for that specific utility, because the load, typically the load mixtures dictate your sensitivity of voltage to energy saved, obviously, then you go full scale. And we've done that, for example, with Excel, where we had, a couple of substations, we do a proof of concept, we did the study, and in the end of the day, we deliver a report saying we predicted that, we installed it, and we do this day on, day off kind of studies to see how much benefits it gives you. And we issue a report to kind of detail the benefits and help the utility to go and build that case. Sorry, that was probably a long answer. But
Last question, if you don't mind. Does the utility then own the infrastructure and service it themselves, or do you have a part in that?
Or do we have, sorry?
Does Varentec service the infrastructure, or does the utility? And then also, do they lease it from you, or do they own it themselves?
No, it's a utility owned and operated. So
Okay.
we basically, they buy it, we provide the training, we provide the platform, And obviously, we provide software support if you need it. But no, it's as if you're buying any other system out there.
Okay. All right. Thank you.
Commissioner. Okay. Professor, very quickly, we had this discussion in the last panel about low-hanging fruit. You provided a very, very thorough overview of grid mod from where you sit. I'll ask you the same question that was asked of the last panel, which is, of all of these different pieces of the modernized grid puzzle that you laid out in your presentation, what do you think, and specifically, from the infrastructure perspective, what do you think that this commission should really be looking at as a major building block for the infrastructure to advance the grid going forward?
That's a good question, because the answer actually comes in many parts. Let me elaborate on that.
Well, you have 2 minutes on the parts.
Yeah. No, the reason I say it comes in many parts is, what exactly are you looking for? Okay. I would think that the first thing to do is invest in infrastructure that improves the reliability of the system. Like, put in enough sensors and protection devices that will make sure that we reduce the frequency of outages and the downtime as much as possible. Because once we have this, other things kick in. Once this infrastructure is there, other things begin to make sense that on the distribution system. That now, once we've guaranteed service continuity, then we can provide quality, because then we can have voltage control, optimization, reduction of losses. But all this becomes moot once if we do not have a reliable system. The reason I'm coming back to reliability again and again is, I have some of you may be aware that I teach at the Institute of Public Utilities in Michigan State. Their Camp Narrook and Grid School. And one of the things that I've had, one of the questions I've had from Ohio commissioners who've attended these courses is, what do we do with the deteriorating reliability in Ohio? Our incidence of outages has increased, our downtimes have increased. And I really think that as far as a lot of areas in the Midwest are concerned, all the way from Ohio to Virginia, is reduction of downtime, automation, distribution automation that is geared toward the reduction of downtime. Another low-hanging fruit is intense tree trimming schedules. It's as simple as that. Okay, that is another thing we encounter in the Midwest.
Very good. Thank you very much. Gentlemen, thank you very much for your presentations. Really appreciate it.